Hi everyone, this is Yichuan Deng, and I'm going to talk about our work on fast distance oracles for any symmetric norms. This is a joint work with Zhao from Adobe Research, Omri Weinstein from the Hebrew University and Columbia University, and Ruizhe Zhang from the University of Texas at Austin. To introduce the motivation of distance oracles, we need to understand the needs of estimating and detecting similarities in databases. This is a basic fundamental problem in computer science, and it has a wide application in some machine learning algorithms, like in optimization, reinforcement learning, discrepancy theory, and covariance estimation. These all leads to the notion of distance oracles. So what is the distance oracle problem? Now imagine we have a data set of some points, which is the blue points in the figure. And then we have a query point Q. Now we need to answer how close this point Q to the data set. So we need to estimate the distance from Q to these axes. This is the formal mathematical definition of the distance oracle. We have to preprocess on the input dataset, and then we read the query point. Now we need to output the estimated distances. So there are different metrics for the distances. The most popular norm, LP norm. And in this work, we study a more general norm, which is called the symmetric norms, where a norm is called symmetric if it is the same for sign flip and the change of the entries. Most widely used norms are symmetric norms. For examples, the LP norms, K-support norms, top K norms, and Orlich norms. For LP norms, the distance oracle problem is well understood based on the technique of randomized linear sketching. So for symmetric norms, trivially answering the query takes time, big O and D. So we ask the following question: is there an efficient and fast 1 plus or minus epsilon distance oracle for general symmetric norms? Here, by efficient, we mean that the distance oracle takes small space and pre-processing time, and it supports fast query and dynamic updates. So let me introduce some complexity measures of the norms. The first one is the modulus of concentration. Imagine capital X be a uniformly distributed point on the unit sphere. We define MCL to be the median of L norm of X over the maximum of the L norm of X. And for K be a subset of N, we define a norm LK to be the L norm of X by taking the first K supports and setting the rest of the entries to zero. Now we define the maximum modulus of concentration, which is the maximum modulus of concentration over all the choices of K. Now we can introduce our main result. So we introduced a data structure which uses n d plus mmc L squared space. Here we ignore the epsilon and log factors, and it supports some operations. The first is the initialization. It can pre-process the dataset in time nd plus mmc L squared. Ignore the epsilon and log factors. And say if we have a query point, our data structure can answer the query in time d plus the size of s times mmc L squared and it provides a set of estimates, which is 1 plus or minus epsilon of the distance. Also, if we want to answer 2 points in the distance between two points in the dataset, this data structure can answer this in MMC L squared time. For our method, we utilized the layer approximation method. To introduce this, we just divide the the entries of the vector into different brackets, and we use the largest number to approximate the vector. So we have several problems to apply this technique to our problem. The first one is the layers will be too much, so we need to induce that. We use the shared randomness to reduce the total number of layers from NT to T. And we store these subvectors, so when it returns some heavy hitters, we eliminate all the false positive ones and subtract the sketches we stored and decode the distance from that. So to conclude, our work presents the first distance oracle for any symmetric norms with nearly optimal query and update time. This problem also raises some questions. The first one is that can we remove these depends on the MMCL, and can our data structure be generalized to some asymmetric norms, and can we extend our symmetric norm distance oracle to any nonlinear metric space? For more details, please check out our paper. Thank you.